Verses from the second epistle to the Corinthians, chapter 9, verses 11 and 12. You will be enriched in every way, so that you can be generous on every occasion. And through us, your generosity will result in thanksgiving to God. This service that you perform is not only supplying the needs of the Lord's people, but is also overflowing in many expressions of thanks to God. In the second part of our lecture on neuroplasticity, we're going to focus on recovery following neuron injury. Abbreviations in this part of the lecture are CNS, central nervous system, PNS, peripheral nervous system, NOGO, NOGO, neurite outgrowth inhibitor, NGF, nerve growth factor, IN, inch, MO, month, and MM, millimeter. A symbol found in this part of our lecture is Ca2+ calcium. If a neuron is injured, and the injury occurs at the soma, or the cell body, the neuron will be unable to survive. A neuron needs a healthy cell body in order to live. When the cell body is injured, the cell body swells up and bursts open. It essentially kind of implodes. This causes the release of large amounts of calcium and stored neurotransmitter into the surrounding extracellular space. These contents are toxic to adjacent cells, so they will cause damage to the surrounding neurons. And this is how an injury spreads and becomes larger. We get this progressive tissue death and damage. Because neurogenesis is limited to only the hippocampus and the olfactory bulb, when we lose neurons, we are unable to replace them. If an injury to a neuron occurs not to the soma, but to the axon, and that neuron is located in the central nervous system, the cell will still usually die. This is because regeneration is not routine in the central nervous system. While new research is challenging this notion, and there are many experiments going on in ways to try and induce regeneration in the CNS. At this time, no relevant regeneration exists in the central nervous system. There are several reasons that axonal regeneration in the central nervous system is not typical and is unlikely to take place. The first is that glial cells, such as astrocytes and oligodendrocytes, release chemicals such as neurite outgrowth inhibitor, known as NOGO. So they release these chemicals which actually inhibit or prevent the axon from being able to regenerate. Other cells produce what are known as suicide enzymes that can cause death of the neurons. Astrocytes and microglia will migrate into the area of the injury and surround it, trying to prevent the spread of injury from a localized area into a broader area. But just like we get scars formed in our periphery, if you cut yourself, a scar can form. The same thing happens here. The astrocytes and microglia form glial scars that physically block and prevent the axon from being able to grow. And finally, within the central nervous system, there is a lack of or a very limited amount of nerve growth factor. Nerve growth factor is required for nerves to be healthy and to regenerate. And the lack of this nerve growth factor contributes to the failure of axonal regeneration in the CNS. In the peripheral nervous system, however, we have a totally different story. Here, cells are likely to regenerate as long as the cell body is not damaged and the axon is damaged far enough away from the cell body. If the damage is close to the cell body on the axon, it's going to be causing some significant changes to take place within the cell body itself. These changes are going to likely be so much so that they actually destroy the cell body and therefore kill the cell. But if we're far enough away from the cell body, these changes are reduced, and the cell body is likely to survive, as is the neuron. Research would indicate that it's about 15% of the length of the axon that is the kind of the key distance from the cell body to predict survival of the neuron. So if you have a 100 millimeter long axon and you damage that axon at 10 millimeters, that is probably going to cause the cell body itself to undergo destructive changes, and the neuron is not likely to survive. But if you are more than 15 millimeters away from the cell body, let's say you're at 50 or 60 millimeters from that cell body, that reduces the impact on the cell body. It's likely to survive, and the neuron itself has a good chance of regenerating and surviving. The process starts by degenerating the injured axon. We have Wallerian degeneration, sometimes also called orthograde. Wallerian degeneration involves degeneration and breakdown of the axon from the point of injury all the way distal to and including its axon terminals. We will also get simultaneously a small amount of retrograde degeneration. This means that there's going to be some degeneration from the point of injury proximal back towards the soma of a distance of approximately 1 to 2 nodes of Neuron-VA. Following the degenerative phase, we now have a regenerative phase. So we have an intact portion of the axon, and this develops a sprout, which is called a growth cone. This is the part of the axon that is going to grow and lengthen, and eventually, ideally, lengthen back to the point that it reaches its target tissue. It elongates at about 1 inch a month, or 1 millimeter a day. So that kind of gives you an idea. If you know where a nerve is injured, you can estimate how long it's going to take for that neuron to reinnervate its structure, its target. So when might I expect this patient to start having sensation again in a certain part of their hand, for instance? The growth cone elongates and continues to grow until it reaches its target, where it then reconnects with that target, forming a new synapse. And this is a required part of the recovery process, because any neuron that does not produce a synapse is unable to survive and will be pruned away. Schwann cells are our friend. They not only secrete growth substance and trophic factors, such as nerve growth factor, which are needed for neurons to remain healthy at all times, but also are needed for growing and expanding neurons. But it also forms tunnels and helps to guide the axons back to the target. The Schwann cells kind of lead the way, if you will. And they're the growing growth cone of the axon simply follows the Schwann cell. Now, not all neurons in the peripheral nervous system are going to make it. In a very good situation, if you were to transect, let's say, the median nerve, we would expect about 80% of its neurons to regenerate and resume synapses with their target cells. There are lots of reasons this might not happen. You could have simply a synapse that occurs but on the wrong tissue. So you could have a sensory neuron that follows Schwann cells that were forming a tunnel for a motor neuron, leading that sensory neuron to a muscle cell, and instead of to a sensory receptor in the muscle cells, leading it to the muscle cell itself. But a sensory neuron cannot activate a muscle cell. Or you could have a motor neuron that follows a tunnel and finds itself synapsing on a sensory receptor. Well, a motor neuron cannot transmit sensory information back to the central nervous system. So these become non-functional. The longer the distance from the point of injury to the target, the more likely just something's going to happen. The extracellular environment's not going to be good. There won't be enough blood supply, so there's ischemia causing cell death. There could be scar tissue that's physically in the way. So the longer the distance, just the lower the probability that you're going to get regeneration and reinnervation. As I mentioned, scar tissue can be a problem. And you can have not just scar tissue that blocks neuron's axon from fully regenerating, but you could have scar tissue actually wrap around and encapsulate the growing axon. This is a condition known as a neuroma. And as I said, you need to be far enough away from the cell body so that the soma doesn't degenerate. And that's going to be, so you need to be at least 15% the length of the axon away from the soma. Here I have put that information on regeneration of a neuron whose axon was damaged in the peripheral nervous system. And I've just put it into a pictorial form for those of you that are visual learners. So in the top we have our neuron synapsing on its target cell, and it had an injury. Following the injury, we get Wallerian degeneration from the point of injury distally all the way down through the axon terminals, and retrograde degeneration for approximately 1 to 2 nodes of Ranvier. The intact nerve then forms a growth cone, and it's the growth cone that elongates and grows, enhanced by the nerve growth factors given out by the Schwann cells and guided by the Schwann cells through tunnels, is directed back to the target cell where it forms another synapse with that target cell, and we now have full regeneration.
And now it's time for a brainstorm. For those of you in the transitional program, here is an opportunity to participate in the brainstorm discussion board. For those of you in the blended program, we will discuss this brainstorm when you are here on campus. This brainstorm question is the following. Would a central nervous system neuron whose axon is injured at its midpoint be expected to regenerate? Why or why not?